Hello students. Before you do these notes, I hope that you have done this Desmos activity. You should have done it in class, but if you, for some reason you didn't, please go back and do this activity first because it's really going to help with your understanding of the fundamental theorem of calculus. So the fundamental theorem of calculus is all built on this idea of areas under curves. And so what we're thinking about is now finding an area of an unfamiliar shape. So let's start with y equals x squared from 0 to 1. So you can see I'm super zoomed in here because here's my 1. So this means this height on my y-axis would be 1 over here as well. And if I took this and divided it into 5 sub-intervals, so I could have 0.2 and then 4, 6, 8, and 1. So I've got my 5 sub-intervals. So each of those would have a width of 1 divided by 5. I went from 0 to 1 divided by 5. So that's where my width of 2/10 comes from. And then I could make rectangles because I know how to find the area of a rectangle. So if I came in and drew rectangles using the right-hand edge of the sub-interval, then my first rectangle would be here. My second one is going to be here. My third one will be here, etc., etc. So here's my fourth rectangle, and then my fifth one is here. So I could find the area of each of these. This first area is going to be, it's going to have a height of 0.2 squared, a width of 0.2. So I'll have an area of 0.2 cubed. This second one has a height of 0.4 squared. Again, my width is 0.2, etc. So I could find the area of each of those. So my total area is going to be 0.2 cubed, 0.4 squared times 0.2. And my last one is going to be 1 squared, of course, is just 1 times 0.2. So finding those 5 areas, I could condense this sum. So I know I've got a sum of 5 terms. So my area of 5 rectangles, I've got each of the 5 areas. The height of each rectangle was my 0.2 squared, 0.4 squared. So these are my different x values, my 5 different x values. So x sub k, so x sub 1 was 0.2, 0.4, etc. And then delta x is my width. So here we had our height from the function, and my delta x was my width. We can see that our estimate is not really reasonable. It's definitely an overestimate because I've got all of this sort of excess space here that I've included in my area, but is not actually under the curve. So when I want to improve this estimate, there's so many things that we could do to improve it. One thing we could do is instead of using the right-hand edge, we could have used the left-hand edge. Then I would have had a rectangle that's not really a rectangle because it has no height to it. I could have had this rectangle, etc. So that would have been an underestimate. I could have tried going from the middle for the height, making rectangles this way. Oops. So through the middle of the height. So that would have been, I would have had bits that were overestimates and underestimates within the 1 rectangles if I had used the middle. I think the best thing to do, though, is to shrink down the width so that I don't have so much that's an overestimate or underestimate. So let's think about if we made 10 subintervals. So if we made 10 subintervals, our area of 10 rectangles would be the sum from 1 to 10. The height would be the f of xi, so plugging in my different 10 x values, not the numbers 1 to 10, but it would instead be 0.1, 0.2, 0.3, etc., times my width, and my width here, my delta x, is going to be 1/10. Because I still have a distance of 1, now I'm dividing by 10. So this, in more general terms, is my delta x. If I made my intervals even smaller, I could say a sub n is going from 1 to n, f of xi, times delta x. So in this case, my delta x would be 1 over n. And as we increase n, we're going to get a better and better estimate. The smaller those rectangles get, the better my estimate gets.